All right, welcome everyone to the last session of AIMOS. Thank you very much for sticking around, and thank you to those of you online. I know this is not a great time of day for many parts of the world, so if you're joining us from other time zones, we especially appreciate that. So I'm Simine Vazire. I'm the moderator for this next session, which is a session with the title Trust in Science, but that title is intentionally very broad. So we thought that for the closing session, we would get some very varied perspectives on kind of the fundamental issue of research integrity and so on. So we'll have 3 talks today in an hour. So these will be relatively short talks. From the perspective, one from an administrator, associate dean, one from a scientist who studies knowledge information networks and so on, and one from a scholar from science and technology studies. So all of them will be connected a little bit, but from very different perspectives. So I'm looking forward to this kind of hopefully mind-expanding end of the conference. So I'll go ahead and introduce our first speaker. Okay, so our first speaker is Mike McGuckin, who is a deputy dean, sorry, not associate dean, deputy dean here at the Faculty of Medicine, Dentistry, and Health Sciences at the University of Melbourne. And in this role, he oversees the research portfolios and has responsibility for people and culture, engagement, and international partnerships. And he's a biomedical scientist by training, and has been heavily engaged in scientific societies and peer review.
Thanks, Simine, and good afternoon, everyone. It's a real pity I haven't been able to come to more of this conference. I'm sure it's been really interesting, and hopefully I can add some interesting thoughts from a academic leadership perspective, but also hear some feedback from you who have been contemplating this for the last couple of days. What have we got up there? No? Okay. So just some context to explain, the environment that I work in. So I'm the Deputy Dean of a large faculty here at the University of Melbourne. It's a faculty of Medicine, Dentistry, and Health Sciences, and it covers everything from social psychology, social work, through all the allied health, biomedical sciences, clinical research, public health. There's a huge variety of research going on across many disciplines. We burn over $400 million in research funding every year that comes in from external sources, from government, industry, charities, individual philanthropists. And on top of that, there's a very considerable investment from the university itself in research and research infrastructure around this. So it's a big undertaking. We've got 2,500 staff, 1,500 graduate research students, 10,000 undergraduate and postgraduate students, many of whom dabble in research projects. So there's a lot of different people involved in research across a big faculty like this. And then we have a multitude of partners, individual researchers and teams working with people locally in the pastoral precinct here, across other universities in Melbourne, nationally, internationally, with other academics, with industry, with all sorts of partners. And that raises lots of opportunity, but also lots of challenges in terms of the way we conduct our research and how we ensure quality of what we do. We have a strong reputation as a health research faculty. We're ranked number 1 in Australia. We sort of rank between 10 and 20 in most of the global measures for clinical and health research. So we have a reputation of being good at it. And with that comes a lot of responsibility for doing it well and doing it with integrity. And that's the topic for my talk, I guess, and just some reflections on that. And just to begin with some thoughts about what's driving culture in our researchers. And there's lots of different things that drive the culture. I like to think that most of our people have come to this career for the right reasons, because they really love science, because they want to make a difference to knowledge, because they want to transform health. If you ask people why they're in this career, they normally start with that sort of thing. But they get caught up in something that's a bit more like a game and a bit more like a survival game in a way. It's very competitive in terms of getting publications and grant funding. and they often talk about it in a sort of survival mode. How do I survive and get from one point to the other? And there's sort of outputs that are required by the system to do that drive behaviour. There is a growing emphasis in health and team-based research, and I think that's a healthy thing because that puts multiple people together, and I think that creates a much safer environment for high-quality research and for trying to avoid people doing the wrong thing. And then we have all sorts of kind of recognition and reward systems that are really focused on individuals and individual achievement. So people are interested in climbing the academic ladder and getting promoted and getting more pay because they do that, or sustaining their contracts, gaining internal funding and support. So there's lots of drivers for an individual to be successful as an individual in this system. And then we overlay on that what the university wants. The university does want to be number one in Australia. It does want to think that it's got a strong reputation internationally because that helps bring high quality students to come and study here. And the esteem of the university is something. So in a sense, the university is driving people in a particular direction as well. And then, what people like me, what research leaders say and communicate, I think is important. And then what I haven't got on this page really is the different microcultures that exist in different departments and schools around. We've got 33 departments in the faculty. They all have somewhat different cultures in the way they do things, and some of that's dependent on history and who's there and the way they follow. And so people grow up in these micro environments in different ways. So there's lots of things affecting culture. And this is kind of how I think about research integrity. And it is something that does keep me awake at night, because that pedestal we're on as a high quality research institute is a pretty fragile thing in a way. And it doesn't take too much to throw that reputation into disarray. And philanthropists and charities and governments and other people who support our research will ask questions if we can't stand behind the quality and integrity of what we do. And the way I think about this is kind of in this bad graph I've drawn here, where we have some sort of continuum between exemplar research practices, and I'm pretty confident that we have people in our environment who do have really exemplar research practices, through to stuff that starts getting a bit more corroded, poor quality things, maybe hubs where lots of stuff is not as high quality. And then at some end of this spectrum is the potential for people actually falsifying and fabricating data. I don't know what the shape of that curve is like. I would like to think the bit over on the right is very high, and the bit over on the left is negligible. But that would be pretty naive, probably. And I think we've probably got a bump in the middle there that's too big. And a lot of that is being driven by the system, and including by the university itself. And if I'm realistic and look at the data that's out there, and you've probably been talking about all of this for 2 days. This is just if it hasn't been shown already at some stage, a survey from the Netherlands, where they took quite a bit of effort to make sure that people responding to the survey knew that their information would be protected from identification. And there's 6,800 respondents there. It's about 10% of the people that they invited. But in the life and medical sciences, this is self-reporting. 10% of people self-reported fabrication and falsification. That's horrendous. And that's those that were game enough to self-report. It must be higher than that, surely. And that is extremely scary. And then over half are frequently undertaking at least one questionable research practice. So if I extend that to our 2,500 people, does that mean I've got 250 people who are falsifying, fabricating data in my environment? I mean, if I've got 2, I'm worried. If I've got 250, I should be extremely worried about this. So and that's kind of reality. There's a lot of other studies out there. This is a meta-analysis of a bunch of studies, many of whom many of which weren't set up as well, I think, to optimize the self-reporting of falsification and fabrication. But there's a considerable proportion of people, you won't be able to read this too well, but fabrication here is 1.9%, 3.3% for falsification, 3.2% for plagiarism, and then these questionable research practices at much higher frequency. So, no matter how good you think you might be, or we might be at the better end of this spectrum, it's still a considerable risk that there's a lot of preventable poor quality research going on, and some sort of undercurrent of falsification and fabrication. We don't have good survey data from our own system, but our early career researchers did run a survey a couple of years ago, supported by us. And these are relatively small numbers. There was only about 250 students at University of Melbourne, Faculty of Medicine, and the Faculty of Medicine at Monash who responded to this survey. And this is the Melbourne data, and its number of people. So 35 of our early career researchers reported seeing non-adherence to authorship protocols. 20 saw selective reporting or publishing. 8 or 9 seeing plagiarism and falsification, and about 3 seeing fabrication. So that's just a small segment of we have many more ECRs than responded to this survey here. And that's in our ecosystem reporting that. And when they were asked, to what extent do you agree that your workplace supports a culture of research integrity? This is data from Melbourne in blue and Monash in grey. You see about 70 to 80% of people agreed with that statement, but worryingly, 15% of people at Melbourne disagreed or strongly disagreed that their workplace supports a culture of research integrity. So we have at least pockets of poor activity facing us. You've probably already been talking with Fiona and lots of other people about reproducibility crisis. This is just some sort of data that was pulled together around reproducibility in preclinical research and in preclinical biomedical research. We think this is a bigger problem than in clinical research, because clinical research went through a transition point some time ago where, publishing protocols, publishing analysis, all these sorts of things became standard practice before conducting major studies. It doesn't mean they're all conducted well, but at least there are, well-accepted guidelines and ways for doing this that are expectations of at least the better journals in the field, and the researchers have adopted those largely. But in biomedicine, there's some sort of reproducibility problem. How big is it? I don't know. This is a paper that tried to estimate the size of it. In the US, they came up with a figure of half of the research being difficult to reproduce, which would be a cost of $28 billion a year in kind of wasted effort through poor quality research. So if you transform that into our University of Melbourne, maybe we're wasting a couple of $100 million a year that's given to us by governments, by charities and others, by conducting research in a less than optimal way. And, they tried to work out where are the problems, and, a big chunk of the problems is in something simple like biological reagents and materials that people are using. Grabbing an antibody from someone in the lab next door and hoping that what's written on the Eppendorf tube is actually what's in it, but without having any validation of that. All those sorts of things lead to problems and mistakes in biomedical research. In a pharmaceutical company, you wouldn't do that. It'd have a barcoded record of what it was, and you'd be able to check on that. But in academic research, the quality filter on that sort of stuff falls away. Some of it in study design, some of it in data analysis and reporting, and some in lab protocols. So what we're trying to do is to focus on research quality. This is not a sort of new concept, but the reason for that is that if you really tackle the quality of research from that standpoint, you are addressing misconduct. I think you're making it less likely it's going to happen, and more likely that if it does happen, it's going to be called out and reported. I think that's probably a much larger part of the problem as well. And when you talk to researchers, when you talk about misconduct, the instant thing they think is, this is not me. I don't fabricate data, and they switch off. But if you talk about research quality, I feel you can engage them because they think at least that that's what they do. They do high quality research and they're willing to engage in a discussion about how they might do that better. So what should leaders do? I've just got a bunch of bullet points here. I'll quickly read through and then I'll finish and we can move on to the other speakers and I can address questions if we have time at the end. I think we need to formally recognise the risk to the reputation and our freedom to operate that's posed by exposure to poor quality research practices and misconduct. Openly discuss that with the community, not just in the research community, but with the wider community, with our stakeholders, and to make a strong proactive stance on prevention and taking action against misconduct. We need to invest a lot more in training programs. This is really where we have a deficit. When we have new PhD students, new postdocs coming to our environment, our intention is to talk about this stuff, to expose them to good quality research practices so that when they go out, they have a different expectation of what they should see, and they're more empowered to call out poor practice when they see it. But that will require quite an investment from us in training up front. We need to expose poor research practices where they occur. And, we're thinking about how we could run audit programs, for example, what they would look like, how we set up an environment where it's much more frequently called out and just becomes part of the standard research culture. Have a vigorous debate about how things should be done. Then we can mandate things, adherence to guidelines, appropriate data sharing. We've brought in electronic laboratory notebooks. One from a point of efficiency, because I think it leads to much more efficient practices in biomedicine, but it also creates this sort of open space where everybody in a lab can see everything that's going on. It's all time and date stamped. You can't delete anything, and it leads to a better culture around research. We need to think about what we do about the problem in preclinical research. And one of the big things is, can you replicate this? And when I talk to researchers about that, they say, I haven't got enough grant funding. How am I going to get someone else to replicate what I do? And we need to tackle that. And the flip side of this is that we're wasting a lot of money so on poor quality practice. So how do we pull that in, spend the money on high quality research, which including on funding replication studies, for example. And then when we reward people, we need to move to a state where we reward things that are long-standing research outcomes that are replicated, well accepted, and rather than a Nature paper or something which may be very sexy for some moments, but may not stand the test of time. And then where research misconduct does happen, we need to be more effective in the way we deal with that, but we absolutely, I think, need to be more open about it. At the moment, it's a very closed shop, and we need to openly report on investigations and our findings. We need to stop researchers moving between institutions in the way that Catholic priests were moved around parishes when they did something wrong. But at the moment, there's a predisposition for institutions to enter into non-disclosure arrangements, and that fights against this. And I can talk more about this if we have time at the end, but we're proposing in the precinct to make a statement around research integrity that brings all of these things forward and involves all the medical research institutes as well as the university. And we're thinking about having a research integrity week next year where we kind of launch all of this. So thank you for your attention.
Thanks, Mike. And we'll do questions at the end after all three talks. So our next speaker is Andy Perfors, who's a professor, no longer associate professor, here in the University of Melbourne Psychology Department, and also director of the Complex Human Data Hub within the school. And he runs a computational cognitive science lab. His research focuses on quantitative approaches to higher order cognition, concepts, language, decision-making, information and misinformation transmission, and cultural and social evolution and change. He also teaches the undergraduate research methods subject, which is a really big undertaking, and he's extremely good at it and loved for his teaching of that class. And he uses R with undergraduate students, so just have to mention that. There's a lot more in his bio, but in the interest of time, I'm going to turn it over to you.
Awesome. Thank you, Simine. And I have to say, I'm really happy to be here. I've intended to come here to this conference many years, and Simine asking me to talk was finally my impetus to come, and it's been great. I was also happy to see some of the talks earlier in the morning, especially Fiona's, where she apologized for sort of being very meandering. Oh, believe me, you're going to see very meandering here. And I basically, and kind of different. I don't actually know how to classify it, whether it's math or philosophy or cognitive science or meta science. Hopefully it's interesting at least. So what I sort of get the sense of what meta science is basically, essentially we're turning our microscope on ourselves, right? We're stepping back and we're using the tools of science to study science. And we've seen a lot of discussion about specific things like this, and many more that I missed here, talking about particular processes we should follow and practices and what will make it better or not. And what I'm trying to do in this talk, I think, is abstract even more than that, and ask ourselves, well, what does it mean for science to work? What's our goal? How will we know if we've achieved it? Or to put it in the sort of words of the session, how do we know whether we can trust our science? And what I'm going to sort of suggest in these 15 or 20 minutes is that viewing science as an information system, I'll explain what I mean by that, is a useful framework for thinking about this question, and I think suggest a few things that are not necessarily intuitive. So there's no citations in here. There's a bunch of bad pictures in PowerPoint, but this is in Paintbrush, actually, not even PowerPoint. I'm old school. But the point is, I think, to sort of encourage a way of thinking that might be useful and a different way of looking at things. So when I'm talking about an information system, what do I mean? I'm thinking in a very, very, very abstract way, right? So we can think of an information system as just the kind of set of components and processes that search through a space of ideas, right? And so ideas, you can think of like, that's just, say, Shannon entropy, some kind of sense of information. And we have agents, things that hold or represent that information, and processes that sort of describe how that information changes. Should I be doing something? Oh, right, yeah. And so the idea is that you can capture a complete system by fully specifying these things. So this is, as you've probably figured out, very broad. You could think of the brain as an information system. The agents here are things like neurons and things that neuroscientists know about, chemicals and stuff. Processes are like, firing happen and neurons die and live and blah, blah, blah. And somehow they're searching through idea space in a way, right? They're representing ideas, and that's changing. What sort of provoked me to think about this is sort of, I spend a lot of time thinking about our global information system. And that's kind of an enormous idea space. The agents are us and also institutions and so forth. Processes involve me tweeting or burning books, or like there's all sorts of, processes that involved. But specifically, we can think of it as science as a type of information system too, right? So the agents are us, but also you can think of agents as, again, it's a thing that stores knowledge or information. So institutions act as agents here, books, talks, and so forth. And the processes are things that change ideas. So right now, there's one of those processes going on, but an individual in their room thinking is also an example of a process. Okay, why am I telling you all this? What is this? So the reason this is useful, I think, is because there's actually a tremendous theoretical machinery that exists to talk about and think about searching through information systems. And that's kind of what science is, right? We're searching through idea space to find the ideas that are right, that describe our world. And so my thought here in this talk is to see if we can take some of the theoretical machinery that a lot of very smart nerds in computer science and math have developed for thinking about search in an abstract sense, and say, what happens if we apply it to thinking about science? So I'm going to bore you here. There's no equations, don't worry, but with a little bit about how we think about search algorithms in general, right? And MCMC is a very common one, but whatever. So the idea is, anytime you have a search, you've got some abstract space. Usually they're very high dimensional. This is a one-dimensional terrible drawing. And what you want to do is you want to sort of search through all the things in the space, and then the y-axis is some value of things on the space, right? So according to this, basically, some things are more valuable than others. Okay, that's all this is meant to show. In a search algorithm, you start somewhere, you move to another part, like the algorithm tells you how, you move around a whole bunch, and so what we're interested in is not just where you end up, but also the path that you've traversed. And in a sense, the volume of the path you've taken, right? So I've traced out some part of the space here. And you can have multiple paths, and a good, obviously a really good search algorithm needs to have lots. The point is that we can actually make statements about what makes a good algorithm for searching a space, even if we don't know the shape of the space, even if we can't always measure everything, even if we don't know a lot, right? You can talk about sort of how they converge or whatever, but you can also talk about, what are good steps and things. And so what I'm going to try to do is take these basic analyses that have been used to talk about computers searching through like the space of protein folds or whatever, and see if we can apply any of those insights to us when we're thinking about how we're doing science. All right, so yeah, just as we can make statements about what makes a good algorithm, we can make those statements about what makes a good system. If we try to conceptualize the system of science here. So this is my attempt to do so. Again, this is all extraordinarily hand-wavy. The point is to sort of make you think. I'm trying to write this up and I have no idea where to publish it because what the hell. But I find it useful to think about it this way, so I thought people here might. So if we're trying to apply this idea to science, then the ideas, right, they're us, institutions, and so forth. The processes are how we transmit information to each other, or how in our own brains, ideas turn into new ideas. This is the dimensions along which our ideas vary. Who the heck knows what those dimensions are? There's very, very complex. It's an enormous, the space of ideas is enormous. The real key thing that I've not specified here, but that you might be wondering about is what the heck is this y-axis, our measure that we're trying to do good on. And I'm actually not going to specify it much because, again, I think you can get pretty far even if you don't. I'm just going to call it goodness, but it could be something like truth. We probably care about that a lot, but maybe there's also things like beauty or, it could be anything. Like if you're Elon Musk, it's how many people, love Elon Musk, like any kind of function we want to maximize. So, so my question is, basically, even, without knowing that much about it, can we say anything? All right, so what are the theoretical characteristics of a good system that we know from the sort of study of these things? So there's a couple things, and I think most of these are going to be fairly intuitive. So one intuitive idea is that a good system, a good algorithm, is one where basically the time that you spend in different parts of the space is kind of proportional to how good they are, right? So if something is good on whatever measure it is, then I should spend more time. My search should spend more time in it. I don't want something like this. That doesn't mean, though, that I'm only spending time on the one best thing, right? I kind of want to sort of touch on all things sort of proportional to their goodness. Another idea is that any good search algorithm, you should be able to get to all parts of the space, right? So there shouldn't be a whole bit of idea space that we just can't get into using our processes and methods that we can't think about. Another idea that a lot of the math on this is sort of that this stuff should converge. So given enough time, if you've searched for a long time, then the path that you've searched for should look like the actual true idea space. It shouldn't be something totally weird or even a simplification ideally, like again, and this is like all these proofs are for infinite time. But as a property about the algorithm, you could say that it is predicted that with enough time it will do that. That's kind of a good search algorithm. Another key thing, I think, for science is that our processes should in general be more likely to go from a bad idea to a good idea, right? Because that's how you get that sort of proportional spending, but not always, right? If you're only ever increasing the goodness, what that does is it means you get stuck in local minima. And if I'm over on one end, I'm never going to get to a really good idea that I have to go through some bad ideas in order to get to. And I think this is kind of going to be key here. And then finally, I say this after watching the whole debacle with Elon Musk and Twitter, it should be robust, not easy to destroy, right? We shouldn't be able to destroy all of science by having one person decide to defund it or whatever. We aren't Twitter. Hopefully that's true. I'm not going to say much about that, but I think any good system is that. All right. What does that imply for science? Again, hand wavy, speculative, but here's my go. First of all, we have to ask ourselves, what is the actual space of ideas? We don't know. I'm going to suggest, with very, very high probability, I'm not confident about that much in this talk, but I'm pretty confident in the suggestion that the space of ideas is something not at all like this. It's something more like this. That is, there are a few ideas that are very good, but lots of ideas. Most ideas are in fact very bad and stupid. And also the good ideas aren't necessarily next to each other. That is, if you have one good idea here, it's actually maybe going to be kind of different from a good idea somewhere else, right? So in other words, there's a lot of space of badness in between goodness. And the reason I'm suggesting this is that we find this when we do computer search algorithms on almost any interesting problem. It seems to be like a fact about the structure of the high dimensional spaces in the world. They have this property, right? So if idea space science is like this, then what that does is it suggests a few things. First of all, these first two points, especially the idea that we should be spending time proportional to the goodness and we should be able to get anywhere, is that diversity is key. And I mean, not just in the sense of diverse people, although that's important, but I mean actual diverse ideas. And what that means, and I think this is hard because many of the processes of science actually fight against it. So there's usually, in most social systems, there's a rich get richer phenomenon where you end up getting a Zipfian thing. The funding is distributed so that a few labs get a lot of it. People are distributed that way, and what you get is then that cuts against diversity. So you have actually most people talking about a relatively small number of ideas. And if we have that, then we're much, much more likely to be stuck in local minima, right? We're not searching all over the place. And this is especially the case if we can't measure goodness easily. Like if we could measure goodness easily, at least we could say, hey, this isn't great, let's try. But as it is, you need to have a lot of diversity, even if ideas are wrong, because that might be necessary to get out of local minima. And another weird, non-intuitive byproduct of this is that communication, I think, is a very good thing in science, but you also don't want too much of it, right? So the problem with, there's a whole literature in cultural change and cultural evolution that shows basically, once you start communicating, that sharpens ideas, but it also basically homogenizes and simplifies them. And if you really want true independence and true creativity, the best thing to do is actually isolate people for a while. They go off, do their thing, and then communicate, right? So a certain style of communication is important. And I think that sort of applies here. If everyone's communicating too much, we're all starting to think the same things. Again, I see uneasy shifting around. Yeah. And I'll also add on the sort of diversity thing that actually I think diversity of processes and methods is just as important as diversity of ideas. It's not just that we have to be in different parts of idea space, but the best algorithms, they are ones that do different things, right? There's small steps, there's large steps, there's sort of totally wacky, weird steps. And they're kind of a targeted mixture where like most of the steps are sort of sensible and smallish, but they have a certain proportion of just total strangeness, right? And I think that we need to think, about how to embed that sort of thing in our science as well. And kind of along the similar lines, it's super important that we have a filter in our information system that makes true ideas, say, more likely to survive, or good ideas, or whatever you want to measure it. You need that filter. If you don't have that filter, you become 4chan. There has to be a way to sort of, tell the difference between a better and a worse idea. But again, it cannot be 100%. We actually need, as a science, to sometimes go from good ideas to bad ideas and have those bad ideas hang around for a while because they might be a step to getting to a better idea farther away in the space. And I think there's this really uneasy feeling about that. But I think it's absolutely the case whenever you have any system with this kind of structure. And I guess where I'd sort of land on myself is that if you look at sort of human children who have to learn things in a world with this structure, I think this is where a lot of play and exploration comes from, right? It's a way of sitting with totally strange things and just playing them out, seeing where they go, right? And so kids, again, a whole set of research on this of sort of kids explore more than adults, they get in random things more than adults, and their learning is slower, but it's actually much more thorough than adults. And I think largely because of this. And this is something that we as a science might want to emulate, right? So if we have too strong or too uniform of incentive structures, so everyone's responding to the same thing in the same way, it might increase efficiency in the sense that, but it makes for a much less robust system, and it makes it much more likely we're going to be stuck in some minima and not even getting to some place that might even be better. So I guess the final thought I want to sort of leave with you is that essentially, I think this kind of way of thinking about it is useful even without specifying a lot of the details. And one of the ways that we might want to think about building trust in the system is by actually trying to take the specific situations or specific properties we can measure and using them as hallmarks of the larger system. So in a lot of things, we don't know what the transition probability is. Is it getting better or worse? For some of the things, we can measure them. And actually, I think a lot of what we've seen in the conference is examples of that, right? We can look at sort of, do people talk about reproducibility or whatever? These are all really good things. But it's probably good taking a step back and saying, what are the other properties that we might be able to measure in the system as a whole by looking at particular things? In the same way that, like, people, ecologists, they don't measure the entire ecology. They look at birds in some place. I don't know what ecologists do. They count seeds or whatever, right? They're not doing the whole system. They're looking at specific things that they've just identified as like key metrics. And I think we could do the same thing for science. And similarly, you don't need to fully agree on or define goodness. You can say, well, it's got something to do with trust. It's got something to do with truth. Here's a stab. And if, convergent, convergent measures should be telling you the same thing. And tell us about the system as a whole, even if we're not agreeing on those things. So I'm going to end there. You could think of where the hell is this talk? It's probably not in these sort of, high, whether it's in a useful random bit or not, I don't know, but hopefully it was interesting. Yeah.
Now I'm going to be really disappointed if there's not a chart with a random squiggly line in the third talk, because that would really unify all of this together. So our third speaker is Sujatha Raman, who is a UNESCO chairholder in science communication for the public good and director of research at the Center for the Public Awareness of Science at ANU. She's trained in STS and public policy studies and is interested in normative questions arising from efforts to bring science and technology to bear on global sustainability challenges. Her current work in the UNESCO chair explores what is entailed by appeals to science as a public good. I'll turn it over to you.
Thank you. Thank you very much, Simine for the opportunity to come to the conference. Yeah, I have the enviable task, I guess, of trying to wrap this up after 5 o'clock. So I'll do my best. So maybe just to start off, a little bit of a disclaimer. Okay, let me see if I can get that moving. Max and I have a difficult relationship sometimes. Just click. Yeah, there we go. Okay, so just a bit of a disclaimer. So although I come from STS, unlike I think some of the STS talks we heard earlier, I don't actually study reproducibility or meta science as a scientific community. But I think that there are meta scientific themes and questions perhaps in STS. And perhaps there's some kind of overlap, maybe there's some tensions in the way in which the meta science community thinks about some of these issues. So in a way, I think I could have used this as the title of my my talk, which is, what can meta science debates contribute to STS-informed work on these issues? But maybe the difference, if you like, is that a lot of what I'm going to say comes at these questions from the perspective of what's important to the public, and what is a public significance of public importance, writ large. So yeah, let me give it a go. I must say my head is now buzzing with some of what Andy was talking about in terms of the importance of kind of diversity of ideas and so forth, which is certainly a strong theme when you look at some of the questions that have preoccupied STS people sort of in my neck of the woods. Okay, so I thought I'd first say a little bit about why consider public good. This is a session on public trust in science. So why even introduce this concept? It's notoriously fuzzy. It can be misused. It can be used in very different ways. Some people would accuse appeals to public good as being kind of really vague, if you like. But I think it's interesting that a lot of the people who have conventionally sort of appealed to the importance of public trust are starting to say, for example, that we need to rebuild trust in science in order for science to serve the public good. So just one example there from the AAAS CEO, Sujatha Parikh, it's an article. He's somebody who's a biochemist, I think, by training. He uses this concept of public good and the importance of science in terms of like serving the public good, if you like. This was certainly a strong theme in, the March for Science that people will be familiar with. But the other organization that I've been engaging with in my recent work, especially in my around the UNESCO chair, is the work of the Global Voice for Science, the International Council for Science. And they have been very interested in sort of like an action plan for science to serve the global public good, if you like. So one kind of answer to this question, why talk about the public good, is, stakeholders in this community are actively linking questions to do with trust with this appeal, if you like, to the public good. So let me connect it to the STS themes that I want to bring into this. So my background, as I said, is in STS. A lot of people familiar with the field will know that, there tends to be a lot of kind of case study based research. And so some people would sort of, stringently object to the idea that there are even any questions that of a meta scientific nature in the field. I probably disagree, as you can tell. And I think there are sort of two particular themes that I want to, two kind of sub areas in STS that I think are relevant to these discussions that we're having at the conference. So one is science for policy, and the other is science that is done, if you like, with the aim of developing new technologies. And I'll give you a few examples in this context. But I think in both instances, one of the aspirations, if you like, of STS work is to put science in its proper place. Is to put science-derived claims about technological fixes also in the proper place. And much of this work has been done in the context of health, environment, sustainability, and so forth, which is certainly where my own interests lie. So here's a kind of summary. Here's the sort of meta-scientific theme, if you like, in a nutshell. So one is this theme that comes across from numerous case studies, which is this hopefully something that most people here will agree with, which is that knowledge is conditional, right? But very often the conditions of particular knowledge claims, particular scientific claims, seem to slip out of view when you look at sort of areas where science gets controversial. And I'll give you some examples. The second point is that knowledge is distributed. And I think this is, again, a theme that has come up in the conference, especially appeals to sort of big team science, open science, certainly. But maybe the other angle here that I would bring in is that there's a lot of interest in the role of the public, in what we might call non-certified knowledge, what that has to contribute in conjunction with science on these matters of public importance. And if I wanted to sort of identify the implications of these two broad sort of meta-scientific themes in STS, I find myself sort of, being pulled in different directions, in opposite directions even. So one is you find in many examples an effort to highlight the limits of science for matters of public policy importance or wider public importance. And here, we draw a distinction between science is important, but science doesn't always have the answers to all kind of policy questions. And so that distinction between the role of science and scientism, that distinction, that's very important, I think, to STS. And the second is, though, pulling in the other direction, and which is a sort of a call for science to contribute in new ways, to do things differently, against the kind of backdrop of our planet in crisis. So again, very quickly, I'll give you a few examples of that. So just looking at the first question of conditionality, the first context of conditionality. If meta-scientists are interested in whether or not certain scientific claims in the public domain, are they true, are they accurate? Obviously that's an important question. But one of the things that STS would bring to that is in what context, under what conditions, right? When does it matter? When do people care about this, especially beyond the scientific community? And I would argue that this is critical for when we start thinking about, the role of public trust, the importance of public trust in science. Just an example here, this is a famous example, a very old one that I've taken from a book by Alan Irwin, the STS scholar, a book that he published on citizen science back in 1995. And one of his many examples was of chemical risk assessment. And the importance of making clear some of the assumptions that underpin claims about safety that were being made at the time, and I would say, continue to be made. One point here has, I think, already come up, certainly in Mark Bergman's talk, which is about the public costs of some scientific norms. So, if you prefer false negatives over false positives in your hypothesis testing, well, that has implications when it comes to environmental matters. And this has been widely talked about. But the other example the other aspect of it that Alan Irwin highlights is the difference between your laboratory tests, what you're doing under controlled conditions, and what happens in the real world. So in chemical risk assessment, for example, there's a tendency in toxicology. The norm is to do single chemical dose response curve type tests. When in the real world, as we know, we are exposed to multiple chemicals that interact. We have sort of low dose exposures over time. And there are questions there about, the claims that might be perfectly true in a laboratory context may or may not hold up when you translate them to kind of public context. And so just maybe one way of illuminating this is, you're studying the impact of a pesticide. You might study that in the lab. You might say, oh, well, this pesticide is safe under these conditions. You wear all this kind of safety equipment, as you can see in that image there. But then, you talk to farmers or farm workers who are actually doing the job of spraying the pesticides, and they might tell you, well, actually, it's incredibly hard to carry out this work. It depends on the conditions. If it's very hot, not very easy to, keep all this protective gear on. And then, of course, here you have another image, which is from Global South context, where the same pesticide that might be approved, and again, under certain ideal conditions, aren't really met. And so in this image, you can see, this person, this pesticide worker is not, the person who's spraying it isn't wearing any protective equipment at all. And so the point here is, you could say that, this stuff about what happens in the real world is separate from science. But I think what a lot of STS scholars would argue is that perhaps there's a responsibility for scientists who are engaged in doing this kind of work, particularly for policy purposes, advising policymakers, when they make claims about safety, this is safe for human use and so forth, maybe there's a responsibility to take into account these kinds of conditions under which the substance is going to be used. And certainly from a public trust standpoint, I think, a number of studies have shown that this is really important. Paying attention to the difference between, your lab conditions, ideal conditions, and the real world conditions. Moving on to the next aspect of the STS sort of themes that I've raised. Another question I think that has come up already in the conference is, are particular scientific claims useful? And I think there's been acknowledgement that even if, in meta science, we are maybe primarily interested in truth or truth value, we are sort of interested in the implications of that for the use of science in public settings, public policy, and so on. One of the questions here that STS would bring to that, sort of elaborating or asking further questions, is useful for whom, with what consequences? If we're talking about new technologies, for example, scientific claims about the performance of new technologies, what are the consequences that maybe haven't been anticipated, so there may be intended, but also unintended consequences. And again, this is a large part of STS under the domain these days of a field that is called responsible research and innovation, tends to be preoccupied with these sorts of questions. And very briefly, to give you one example, countless case studies, again, like I said, the field is filled with lots of case studies. One area that I've been involved in, done some research on, is on gene drive. And so you can see there are a couple of examples, newspaper articles, these from The Guardian, I think, about the ability, the proposal of using CRISPR, of using gene editing to create what are called engineered gene drives, and to use them for the purposes of, for example, eliminating malaria in global south countries that are affected, or closer to home, controlling invasive species which people from Australia and New Zealand will know, it's a huge issue in this side of the world. And the question here, and this goes back to the diversity question that came up in the previous talk, the big question here is who is actually involved in making these assessments of these technologies? Should they be the same scientists who are involved in developing, maybe advocating the use of the technologies? Can we be confident in their abilities to, capture all the kind of epistemic issues, let alone, the value questions and the ethical questions that come up in relation to these sorts of issues? And I guess it's fair to say, there's been a long-standing kind of recognition that, wider engagement, public engagement is really important for doing this kind of technology appraisal in a way that is, as far as possible, dispassionate. What we find, I could skip over this, some of this, but just want to highlight here is that the research that's been done in this area, again highlights that very often people in communities, members of the public, have epistemic questions or potential epistemic questions, as well as concerns about the ethics and values and so forth. And so just one example of the gene drive for malaria case, people have done research in Uganda where people in the communities were very interested in this technology. They were quite fascinated. I mean, these were communities that are affected by malaria. And so, for obvious reasons, they were keen on the prospects, but equally raised these kinds of questions. What's the role of mosquitoes in the ecosystem? If you want to translate it in those terms. Which animals rely on them for food? What might be the unintended consequences of eliminating one species? Could that open up, create an opening for new diseases to emerge? And I think we can all agree that these are reasonable questions to ask, but we're not being considered in the standard sort of risk assessment approaches. Okay, so just to kind of wind up here, I want to just point to one of the ways in which the public good question is being posed in ways that I think, by contrast to the two examples that I gave so far, they've highlighted in some ways the need to put science in its proper place, right? To need to recognize what science can or cannot tell you, the limits, if you like. But I think what we're seeing now in these kind of public good invocations around science, and I'll just give you a couple of examples here. When it comes to issues around the planetary crisis, one image there is about the so-called triple planetary crisis of pollution, climate change, and biodiversity loss. Others in Stockholm Environment Institute have highlighted the fact that we are overstepping a number of planetary boundaries. The International Science Council has really sort of responded to these concerns to make an argument that a lot of science funding supports research. This is, a quote from one of their reports, that's actually limited in its ability to respond to these big challenges, the big challenges that we face today. So they highlight, their claim is that science is too fragmented, it's too compartmentalized, it's too narrowly focused. And if we want to do science for the public good, we need to find ways of engaging across, if you like, research that's about nature, about biophysical phenomena, and integrate them with knowledge and research about social equity, about global justice, and so forth. So that's a tall order. That's not easy. That's not going to be easy to do. But what I want to kind of conclude on is that I think it's interesting that there's a whole part of science in this kind of broader sustainability science or environmental science domain, where some people are starting to make those connections. I've just got a couple of examples there. One is from Nature Climate Change, where scientists are warning not just about greenhouse gas emissions, but about affluence and the growing inequality in the same breath. You see in the other image there, people are, some scientists have said, well, it's not enough to put the biosphere, when we talk about environmental change, it's not enough to put the biosphere at the center. Maybe we need to start with a recognition of deep social inequalities and then look at the impacts on biological or environmental phenomena. So that's just my last slide. A bunch of questions there to sort of highlight the fact that, here's this sort of effort, if you like, to integrate the biophysical and the social. There's calls from these big institutions, as I showed, to, carry out this work. And perhaps a meta-scientific question for the future is, what are the norms of good science in these kinds of contexts? Is it something that we should dismiss because it seems to sort of detract from, maybe concerns we might have about scientific independence? Or is there something there that we should be thinking about, maybe redeveloping, maybe thinking about new norms for doing science in the context of planetary crisis? And I will stop there. Thanks very much.
Ask actually the speakers to come up here so that we can just take one or two quick questions, if that's okay. I don't know. Is it okay? Great. So yeah, I think this has been a really interesting set of talks that are very, very humbling about, how hard it is to do good science and to even define what is good science and threats. internal to science and external and so on. So I'm excited to hear what thoughts and reactions you all have. Yeah.
About information theory, science, consider the implications of the Shannon's idea of mathematics and communication in terms of those process lines that you're talking about. I think there's a space for that to be applied on, there's the line there, and you have the observer line going back over.
Yeah. So, I mean, I glossed over.
Sorry, we should restate the question, but I can't restate that question.
Sorry. Basically, the question was whether I'd sort of thought about this in terms of like Shannon entropy and sort of theory of information transmission. And I kind of glossed over all of that, but that's actually where I started. So a lot of what I study is the evolution of information systems, which is usually done in exactly that framework. So yes, I could go on lots and lots, but I think it's pretty compatible with this notion, and thinking about things like selection pressures for different information and where signal loss comes from, and redundancy of the system. That's where a lot of the sort of a lot of stuff in information theory is about that, and that's where a lot of the sort of my claims about like why we don't want to be just all in one place is because of like redundancy of signal and stuff. So yeah, sorry. Patrick.
Just to follow up on that, and thanks for the presentation. So it was very creative, very well related. If there are different agents that think through idea space, like there are different people making different steps, right? Computer research is a journalist institution. How do the prescriptions of information theory apply to different big steps, small steps?
Okay, well, so so there's two different sort of things. You can look at, for any individual agent, what are the steps they make, what is the information sort of transmission properties of that? And then I think, again, then you can say, as a system that is made of these agents, then what does it look like? What is the shape of the space that they've done? Again, I'm sort of taking stuff that's very mathematical and applied to particular contexts and doing hand wavy-ish sort of applications to science. We don't know what the actual shape of science is or what the actual agents are, but that's the idea is, yeah.
I'll ask a question quickly to Mike, which is, after hearing the other two talks, what do you think the challenges that these ideas present for, relatively simple structures like incentives in academic departments or faculties and so on? If we need a lot of diversity and we need to consider all these factors outside of science.
Yeah, it's enormous. I'm still cogitating on your talk, Andy, and I'm sure I will do that for some time. But I think how do we set up a situation where we're open to ideas and we don't have a lot of groupthink, because in a way that's what we institutionalize. People thinking the same lines, and huge labs that are focused on the same sort of trying to prove the same idea over and over again. And a lot of that comes through security, and some of the classic places where they've really made inroads in science, people have been given time and space to think and work, and not being a victim of this sort of grant system churn. And then I think I was reflecting during your talk on our people who did the modelling around COVID for the government, and that's mathematical modelling. They're very good at it, and they were well set up to do it prior to the pandemic and planning for it. But then they have to give this complex set of sort of stochastic possibilities to a government. And when ScoMo said we're going to trust the science, so the sort of shudder went down my spine, because I thought, are they going to blame the science when things go wrong? But talking to those people who went into this project with the government because the country had a need to get high quality information, but they had to sign confidentiality agreements. What they told the government didn't always eventuate into what the government then said to the public about what they'd been told. And so you get this whole, then there's no right answer anyway in everything that they were informing the government on. So this is hard, and there is no simple truth in science. There's evidence that we accumulate and ideas that grow and disappear, and often things that are tenets that things are built on are disassembled at a later time. So we've got to allow all of that to happen in an ecosystem, I guess. So that's a random answer to your question. Yeah.
Maybe a good note to end on. For those of you who are not Australian, ScoMo was our prime minister, who was not known for his support of science. All right, well, thank you to our speakers. Please join me in.